Thank you very much for that lovely introduction. Fundamental physics, actually. Physics itself is an enormous field, and I'm going to talk about a small portion of physics, which I call fundamental. But first, let me just say how pleased I am to be back in Singapore, which, as KK said, I've come many times. It's a wonderful place. My wife and I have been in Malaysia for the last week at the Asian Science Camp, which brings young students from all over Asia, not just Southeast Asia, but Asia as a whole. But we were very happy to have the opportunity to stop off for a day or two in Singapore on the way home. I've been to this science museum. I was confused, not SMU, but CSU, or the Science Museum before. It's an incredible museum out there, and I'm sure very inspiring to young kids. So I'm going to try to just give you a sense of some of the questions that we're exploring at the frontiers of fundamental physics. The frontiers are where our knowledge ends and our ignorance begins. But first, I remind you how much we have learned in the 50 years since I got my PhD degree. It's quite amazing sometimes to go back and realize, my God, how ignorant we were 50 years ago. Now, we, of course, I worked in the field of elementary particle physics, whose goal is to discover, understand the basic building blocks of matter and the forces that act on them, the theory of stuff, what it is, how it works. And in these last 50 years, we have really perfected a theory of matter, a theory that realizes the microscopic understanding of the atomic structure of matter. But 50 years ago, although we knew that atoms and molecules were the basis of ordinary matter, we didn't really understand the structure of the atom, especially the structure of the nucleus that is at the center of all atoms. So as you know, an atom consists of a very small nucleus where most of the matter and the positive charge lies. But the atom itself is really a cloud of electrons surrounding this nucleus, and the properties of atoms and molecules have nothing much to do with what goes on inside the nucleus. So for the 50 preceding years, we had developed a theory of atoms and molecules based on quantum mechanics, which underlies our understanding of ordinary matter. But until we started constructing large accelerators that collide protons together and allow us to probe matter at very short distances, we really had no understanding of what went on inside the nucleus, except that the nucleus was made out of protons and neutrons, but what protons and neutrons were made out of, we didn't understand. So in this next 50 years, we truly identified the fundamental constituents of matter, which, in addition to the electrons, consist of quarks. We understood that the nucleons were actually composites of quarks. Particles that had never been seen in isolation were kind of weird, but they do make up the nucleons, 3 quarks per nucleon. And most importantly, we understood in a deep fashion the forces that act within the atom and the nucleus. The force of electromagnetism goes way back to the 19th century, our understanding. Indeed, it was James Clerk Maxwell, whom this hall is named after, who finalized the theory of electricity and magnetism the basis of the Industrial Revolution, and the basis of our understanding of atoms and molecules. What holds the electron in place is the force between the electron and the charged protons, the nuclei in the nucleus, which is a force, an electrical force. Of course, we need quantum mechanics to truly understand the atom, but the force is the force of electricity and magnetism. The force that acts on the nucleons, the proton, the neutron, and ultimately, as we discovered, the force that acts on the quarks that sit within the proton and the nucleon. 50 years ago, when I started doing research, was totally mysterious, and nobody knew what it was. But now we do. And the remarkable thing that was discovered, I'll say a word or two about, is that the basis of that force was a generalization of Maxwell's theory. So Maxwell really was the founder of all of the forces we've understood now. In the case of electricity, you know that the force of electricity is a force between charged particles that carry electrical charge, like the electron, the proton. The strong nuclear force that holds the quarks together is very similar. It is a force between quarks, which carry 3 charges. So the nuclear force is 3 times more interesting than the electrical force. There are 3 charges, gives rise to a more interesting force, but it's the same kind of force as the force of electricity and magnetism. For reasons which I'll briefly mention, it has different manifestations because of quantum mechanics. And then there's the weak nuclear force, which also turns out to be a kind of generalization of Maxwell's theory. So Maxwell was more important than even he knew. But we've learned a lot in other fields of physics as well. The 2 fields I want to briefly mention, discuss the frontiers later, is astrophysics and cosmology, and condensed matter physics. In the last 50 years, we have been able to reconstruct almost the complete history of the universe. 100 years ago, astronomers, physicists had no idea what the universe was and its history. It was thought to be static, eternal, and unchanging. Now we know that it's changing all the time, and we have mapped out its history. This is an iconic picture of the history of the universe. Time starts here, 13.7 billion years later. We live in an observable universe with 100 billion galaxies. The universe started somehow, expanded rapidly, settled down to a more or less constant expansion, and now is undergoing a period of accelerated expansion. I'll say a bit about the challenges in completing this picture later. And finally, the realm of atomic, molecular, quantum mechanics of ordinary atoms, we have made enormous progress in both understanding and using that understanding to control matter, ordinary matter, new kinds of matter, artificially created matter, down in all of its different phases, down to the scale of atoms themselves. Atoms once invisible are now quite visible. Not only can you see atoms, you can manipulate them, pick them up, move them around, create a corral of atoms on the surface of a metal, and see the waves that exist in this corral of atoms. And I'll discuss some of the issues in this field later. What I want to stress, however, is the most interesting part of science, in my opinion, is not so much what we know and have learned, proud as we are of these achievements of 50 years, but rather the questions that remain open, the new questions we ask. That's what drives science forward, motivates young people to go into science. It's the unanswered, open questions. That's what defines the frontiers of science, what we don't know. So I provocatively like to say that the most important product of knowledge is ignorance. This is supposed to catch your attention and say, what do you mean by that? And of course, by ignorance, I don't mean the ignorance that leads to bigotry and racism. What I mean is informed, new questions that can be answered by observation, by experiment, and by theory, the scientific method. What I mean is when I started doing my research, there were many wonderful, interesting questions like, what goes on inside the proton? What are the laws of force? What is the proton made out of? Those are wonderful questions. Those questions have been answered. But in answering them and having answered them, we're now smart enough to be ignorant in new ways. New questions arise that we didn't know enough to even ask 50 years ago. And that's what drives science forward. Informed ignorance. So let me start discussing some of those questions. And let me start at the beginning, the real beginning, the beginning of the universe. You see, in this history of the universe, there's some place where things are kind of fuzzy. Somehow the universe began. The universe is expanding. If we run the movie backwards, which we can do in two ways. One, as theorists, we can take our knowledge and make time run backwards on pencil and paper. But two, we have another way looking into the past to see what the universe looked like, and that is looking at light that has come from so far away that it had to originate 13 billion years ago. And we actually have the baby picture of the universe. A picture of the universe the way it looked 13.5 billion years ago, and here it is. If you look at the right spectrum, the microwave radiation coming from very far away, it's been traveling for 13.5 billion years, what you see is a picture of the universe shortly after the beginning, whatever that is. And it's a pretty boring picture. There are no features. You can't see any nose, mouth, anything. It's in fact almost a perfect hot gas with no structure. The only thing that defines it is its temperature. In fact, it's the most pure black body object created. We can't get something as pure in the laboratory. It just looks like a hot ball of gas. And this is a bit problematic because if it was a pure hot ball of gas, it would expand, the universe is expanding, cool off, but nothing would happen. There's no structure. To get structure, you need something with structure to begin with. Where's the structure? After this Nobel Prize winning discovery was made, people mounted experiment after experiment to look for structure in this hot ball of gas. And finally, instruments were good enough to pick out another Nobel Prize, to pick out at the level of 1 part in 100,000 structure in the microwave background. And this is a picture of that structure. You see there are spots here. The red spots are regions where the gas and the particles were denser, hotter. And then there are regions, the blue regions, where the gas was colder and less dense. Gravity is attractive. That leads to an instability. If you have a region which is dense, it will collapse. The particles will attract each other, and those will collapse. If you have another region which is less dense, it won't collapse as fast. So that's unstable. These regions will collapse. These will collapse less fast. And you can run now, starting with these small fluctuations, these small perturbations in otherwise a perfectly homogeneous gas. See what gravity will do if you wait 1 billion years or so. And this is what happens. Those regions collapse, the denser regions become denser and denser, and now you see the matter, particles, are all concentrated on sheets and filaments and very dense regions. And once these particles, electrons and protons, come together, they form atoms. And when the atoms come together, the nuclei come together, they undergo fusion, nuclear reactions, and start, like our sun, emitting light. And they stabilize and form stars. And the stars attract and they form galaxies. And with our knowledge of physics and our theory of an expanding universe, we astronomers, astrophysicists, are able to show how the structure of galaxies and stars and clusters of galaxies that we see when we look out throughout the universe arise. An incredibly successful theory of the evolution of structure and the evolution of our universe. The moment, 13.7 billion years later, we live in a universe where we can see 100 billion galaxies. It's expanding, and recently we've discovered that that expansion is accelerating. But how did it all begin? And if we try to use our theories, including the modern string theories, whatever we have, at the very beginning, everything goes haywire. Our theories break down. We don't know. So this question we have is totally open. And it's a pretty interesting question. It used to be a question that only was asked by religion or philosophy, but now it's science. We know enough to know that this question can be addressed, maybe by observation. Maybe there are ways to look back and see signals which came not from 300,000 years after the beginning, but a second after the beginning, or a billionth of a second after the beginning. And one way of perhaps of probing way back to close to the beginning is using waves of gravity. Whatever happened at the beginning produced waves of space-time, of dynamical space-time. which is what Einstein taught us is gravity itself. So we have the possibility, hopefully, with amazing detectors that are being planned to be situated in space, perhaps to look for gravitational waves which will inform us of what was going on very close to the beginning, whatever that means. But this question is really interesting. Physics has never asked this question before. We didn't know enough to ask such a question. And it's not clear that physics can answer this question. Can physics really tell you how the universe began? What was the initial condition? We don't know, since we've never had to ask such a question before or been able to. But it is now a scientific question. And it's not an easy one, because when you think about it, you're asking, how did time begin? Well, people then ask, what happened before time began? And maybe it doesn't begin. Maybe it's cyclic. Maybe the universe expands and then contracts, and it's cyclic. Goes on in a cyclic fashion forever. And maybe, which is what I suspect, we don't really know how to ask the question correctly. That's often the case. When we figure out how to correctly ask the question, the answer might be easier to find. But in any case, this is now science. And the experience of science over the last few hundred years is that whenever you can pose a question and address it by the scientific method of observation and measurement and theory, like, for example, what is life? That was also a question addressed by religion and philosophy before we developed modern chemistry and atomic physics. And now we know the answer to that question, what is life? We don't know how life works in all of its details, but we know what life is. And that is a question that is now scientific. Astronomers also have informed particle physics and told us that something is missing in our theory of quarks and electrons, because they discovered that there's dark matter out there in the universe, which is not described by our theory of matter that we have observed on Earth. They also tell us that there's a lot of energy in the universe that is what, well, they tell us that the universe has this accelerated expansion, which presumably is due to what sometimes is called dark energy. And these two things, these two dark entities that fill the universe, pose an enormous challenge to our understanding. Dark matter is the most obvious. And we don't know what this dark matter is. The only way that astronomers have observed it is indirectly. Any kind of matter attracts other matter by gravity. All matter attracts other matter by gravity in Newton's theory, in Einstein's theory. And when astronomers looked at our galaxy and measured the velocity of stars going around the center of the galaxy, they could use our understanding of gravity to calculate how much mass there was in the galaxy that pulled the stars around. And they discovered they couldn't see enough mass to agree with the observed orbits of the stars, concluding that there had to be more mass that's invisible, therefore called dark matter. And according to these calculations, many, many galaxies and clusters of galaxies our galaxy really looks like this if we could see the dark matter with our eyes. If it emitted light, we could see it, but it doesn't. But from gravity, we can infer its existence. So our galaxy really is a spherical bubble of, held together gravitationally, of dark matter. And the matter that we're made of falls into this dark matter galaxy, forms stars, radiates light, that's how we see it, but is only about 5% of the mass of the galaxy. Here's a remarkable picture which convinced many of us of the existence of dark matter. This is the collision of two clusters of galaxies, which a few billion years ago collided far off in the universe, and astronomers have taken this picture. Now you see two kinds of matter here. Red matter, it turns out to be visible in the X-ray emission of ordinary matter, and the blue stuff represents dark matter, which is observed indirectly by the fact that the light coming from behind this cloud of dark matter is bent by the dark matter. A massive object can bend light. Light is attracted, it's bent around the matter. And so if you look carefully at the various blobs here, which are bright galaxies farther off behind the blue blob, sometimes you see multiple images because of the bending of light. And astronomers can use that to measure the distribution of the dark matter. And this is the blue stuff here. And in this collision, what happened was that the red matter, visible matter, has friction because it interacts strongly with itself, so it slows down, but the dark matter just keeps going, and these visible matter and dark matter separate a bit. In a billion years from now, they will pass on, and the visible matter will fall into the center of the dark matter. This is the dark matter. But what is this dark matter? Well, we don't know. But it's there, so we have to figure out what it is. And people have been trying and are currently trying and getting close, I believe, to discovering dark matter by observing the wind of dark matter that's passing through the Earth, passing through this room, passing through you. There are hundreds and hundreds of dark matter particles passing through your bodies every second, moving 500 kilometers a second. I don't want you to get worried. They interact very weakly. They just pass through without doing anything, so you're safe. They're not going to cause cancer. That's good, but if they did cause cancer, then we could detect them, so that's bad. So you have to construct a detector way under Earth and wait a long time to see one collision. Just like neutrinos. We have neutrinos we can detect, but they can pass through the whole Earth without hitting anything. But people are trying to detect them, or another way is to make them. Einstein taught us that if we have energy, we can make matter. So with enough energy, you could produce the dark matter in the laboratory. And places like the LHC at CERN, they're trying to produce and detect and measure the properties of dark matter. And I think this is very likely to be solved in the next decade. Dark energy is a different kind of problem. Dark energy, presumably, is what is responsible for the accelerated expansion of the universe. And we sort of know how that can happen because Einstein's theory of gravity tells us that if the vacuum, empty space, has energy, then it will make the universe expand in an accelerated fashion. And there's no reason why empty space shouldn't have energy. But we don't know that that's the right explanation either. And we don't know whether that energy in the vacuum, in empty space, is there forever or just temporarily. Which really means we don't know whether the universe will expand forever. I started out asking questions about the beginning of the universe. But you know, physics at the basic level looks the same whether you run the movie forward or backward. And I'm actually just as interested in the question, how will the universe end? If you really have a theory, a good theory of the history of the universe, you should not only understand how it began, but how it will end. And that's open. If the acceleration is due to a constant cosmological constant, then it will expand in an accelerated fashion forever. And then, by the way, it'll never end, but it'll become pretty weird. Because all the other galaxies, all the galaxies in the universe will be moving away from each other with larger and larger velocities, and eventually with velocities greater than the speed of light. So in 100 billion years, were you to step out at night and look at the sky, it'll be black. The only stars you will see will be those in our own galaxy, bound by gravity. The rest will be moving away so rapidly that they can't communicate or send light to us. Pretty interesting. And if you keep going more than 100 billion years, things get even more unusual. But I'll stop here. So how does the vacuum get an energy? There's nothing in the vacuum. It's empty. And if you think about the vacuum, well, classically, vacuum by definition is nothing. Empty space. Nothing there, so no energy. Energy, mass, is the source of gravity, so classically, no expansion of the universe. This is the classical description of the vacuum. Pretty boring. But I want to show you what the vacuum really looks like. And the reason the vacuum is interesting, the reason it's a complicated medium with structure is because of quantum mechanics. See, to say that the vacuum is empty and there's nothing there, Heisenberg, quantum mechanics taught us, what do you mean by that? How do you know that the vacuum is empty? Well, I know because I look. But what does looking mean? You have to probe it. You have to send it a probe. And when you do that, you disturb the vacuum. So it can't be just at rest. You know, quantum mechanics, we have the uncertainty principle. In classical mechanics, you can have an object like this, which is at rest here, a definite place, and it's not moving. It has a definite velocity, a definite momentum. But that's impossible in quantum mechanics, right? Because Heisenberg explained, to know that this thing is at rest and not moving, I have to observe it, right? I send in a beam of light, bounces back, I know where it is. I can measure its position and its velocity. But the very act of measurement disturbs it. I hit it with a beam of light, it recoils a bit, so it's moving now. quantum mechanics, there's nothing that is at still. There's no state of the vacuum with no particles or no fields. They're always there, fluctuating a bit. We call that 0 point motion, even at absolute zero, the temperature, nothing around. So this is actually what the vacuum looks like at the scale of a proton. This is 10 to the minus 33 centimeters, about the size of a proton. And if you could look with very good microscopes, which is what our accelerators are, in effect, you would see, and you could see the chromodynamic fields, the fields that give rise to the forces between quarks. They would be fluctuating, much like is pictured in this calculation using the theory of the strong force, quantum chromodynamics. This is a better picture of the vacuum than the empty screen. And this has many effects, including asymptotic freedom. If you take two quarks, turns out that the force between them, when they're close together, asymptotically close, is weak. Weaker and weaker as they get closer. But because of the properties of this complicated vacuum, quantum mechanical vacuum, and these fluctuating fields, the force between these quarks gets stronger as you pull them apart. Very strange phenomena. And it's completely a product of this quantum mechanical structure of the vacuum. That's asymptotic freedom, which, by the way, somebody, yes, you remarked that that's a good name. It's indeed true that it's very important in physics to find good names. But I'll tell you a story about asymptotic freedom. So a few years after this came about, I was in Moscow at the Lebedev Institute. I was giving a lecture. This was not a good time to be in Russia, Soviet Union. I was put in Sakharov's office because Sakharov had been exiled to Gorky. I gave a lecture on QCD, and of course, sometime in the lecture, I wrote asymptotic freedom. Gets more interesting. The lecture went fine. After the lecture, it turns out, I didn't know this, the next day, there was a meeting of some of the Russian physicists, which was kind of they're trying to organize to discuss Sakharov's expulsion and how they should react. And there was somebody who took a picture of this meeting. And the blackboard with asymptotic freedom written was in the background. And the next day in Pravda or Izvestia, I forget, this picture appeared. And I was told later that the director of the institute was brought into the KGB to try to explain what is this asymptotic freedom. I once gave a lecture at Princeton called Asymptotic Freedom for the Masses. It's a good name. Anyway, in the theory of quantum chromodynamics, this is what happens when you pull quarks apart. You see there are flux lines, lines of force, very much like in electricity and magnetism. But in electricity and magnetism, these lines would go out. You know, you've seen these lines of magnetic force field lines. But the quantum vacuum pushes them inwards to form a kind of flux tube, a fat string. And because of that, there's no way of separating the quarks. It would require an infinite amount of energy to separate quarks, which really is the explanation for why no one has ever seen a quark, even though they're there inside the proton and inside other particles. And it also explains why the force gets weak at very short distances. And that led me to Stockholm. I wanted to show you this because you see the king giving you a bunch of things here, a medal and a check, and a beautiful document which has a picture with a picture drawn by a Swedish artist here of 3 quarks, different colors, bound by the strong force, unable to get out. This is what it actually looks like if you do the calculation. Try to pull the 3 quarks out of the proton. But these fluctuating fields do something else. This vacuum clearly has energy. You see there's all this stuff moving around. It's got a lot of energy. So in quantum relativistic quantum mechanics, we understand that it is very unlikely that empty space has no energy because it's always full of these fluctuating fields which have energy. And in fact, if you just estimate how much energy there is in empty space from the strong fields, QCD, or from just about any other physics you can think of, you get an enormous amount of energy. So much so that the universe would have expanded so rapidly that every atom would be all alone. That clearly hasn't happened. And in fact, the measured value of the energy, the vacuum, is off by 120 orders of magnitude. Well, that's a theoretical problem. You know, we can't calculate this number, so it's very small. But why? And that is an enormous challenge which we don't know how to answer. And that's one of the hardest problems. And so far, there are no good ideas. Might even be harder than, and might be connected to the origin of the universe. If we understood how the universe began, we might understand how it began with this incredibly small number. Anyway, we have this wonderful theory, standard model or theory of elementary particles, quarks and leptons, and the forces that act within the atom and the nucleus. And the final part of this theory is something called the Higgs mechanism, which I won't try to explain, but you probably have heard the word. And the particle predicted by the simplest form of this additional force was discovered 2 years ago, 3 years ago, 4 years ago now. And this is an incredible theory. But I don't want to talk about success. I want to talk about questions. And one of the obvious questions that arose right after the completion of this theory was, how do the forces unify? Do they unify? Because the nature of all these forces, as I said, are kind of generalizations of Maxwell's theory. They're the same kind of force. The strong force is much stronger than the electromagnetic force, but as you go to shorter distances, higher energies, it gets weaker. Asymptotic freedom. And the electromagnetic force gets stronger. That's reasonable. The closer together, the stronger the force. This is the weird one. But maybe, if you extrapolate, they're the same. And indeed, people extrapolated the standard model right after it was completed and discovered that all the forces come together at a very short distance. If you could do experiments at the very high energies necessary to probe these very short distances, you would see that this really was one force. And all these different kinds of quarks and electrons would all be one kind of matter. That picture is very appealing and is consistent with everything we know. There's really nothing we definitely know that says that that's not the case. Not only that, the force of gravity becomes a strong force at those distances. Gravity is a very weak force. Some people find that strange because it's the only force they feel. You get up in the morning, But gravity in the atom is 10 to the 40 times weaker than electricity. The reason you don't feel the electromagnetic forces, unless you're very unlucky to be hit by lightning or something, is that electrical charge can be screened, neutralized. If you have a nucleus with positive charge, it immediately attracts an electron and becomes a neutral atom, which gets rid of the charge that was the source of the force. If you have a quark with a color charge, it attracts other quarks so strongly that you can never pull them apart. If you have, however, a mass, an object with mass, well, there's no object with negative mass. There is no such thing as anti-mass or anti-gravity. You can't shield gravity. It just builds up. So here's an experiment that shows you how weak gravity is. The experiment is this. I'm holding this up. Why is that? Prove that gravity is weak? Well, think about it. What is pulling this down? 10 to the 54 atoms in the Earth are all pulling on this pointer. And with a little bit of electric force coming from the chemical electromagnetic force-generated interactions in my muscles, I'm countering all the atoms on the Earth. So the electric force is very weak. Gravitational force is very weak. But the charge of gravity is mass or energy. And when you get to energies, which are 10 to the 20 times bigger, the force is 10 to the 40 times bigger and the same as the other forces. So that is the clue that has led many of us to try to unify all the forces of nature with gravity, but at distant scales that are so small that we can't probe them directly. We have to speculate. We have to try to answer some of the questions we can't answer with a standard theory using a unified theory. And that's led us to very strange new speculations like string theory, which originally we thought was a revolutionary new way of looking at matter. Instead of particles, we would have extended objects, unified as together in the dynamics of an extended string. And although 30 years ago we thought we were close to using that new way of discussing matter to construct a unified theory, we've discovered, as often happens in science, that the mountain of knowledge is higher than we thought. And we've climbed many peaks, but the top of the summit is still far away. I'll discuss some of the obstacles or insights we've led to in a moment, but the way we try to get direct clues as to what really is going on is by observing and measuring at instruments like the Large Hadron Collider, the Large Particle Accelerator in Geneva, outside of Geneva. This is the Geneva Airport. This is a 20-kilometer tunnel where we collide protons at almost the velocity of light. They move around the circular tunnel, they collide together, they violent events, and we measure, take photographs of what comes out in these enormous detectors. We look for new physics there. But for theorists like me, we probe whether we could unify the forces using our speculations and ideas, and in particular to describe all the particles and all the forces arising from the dynamics of a single object, a stringy, extended object, superstring. String has many different vibrations, so it could describe many different particles. And that understanding has gone very far. I'm not going to pursue that for lack of time. Instead, I'll tell you about some of the insights string theory has led us to about time, about space, and about time, which are the most fundamental concepts of our understanding of the natural world. If you think about it, what would you do without space and time? In fact, you need space and time so much that as infants, even before you could talk or do very much, each of us constructed a model of the world, a theory of the physical universe, which located objects in space and change in time. You were never taught about space in school. You knew it. Space exists. You move in a three-dimensional space. You were never taught about time. You were taught how to count time, right? The clock. You were taught how to measure distance with meters. But the basic concepts of space and time, if you think about them, were invented by each of us as our brains were developing as infants. And they're basic to our formulation of physics. Now, we have already, in the last 100 years, modified our notions of space and time. Einstein taught us in his theory of special relativity, and then general relativity, whose basis is that space-time itself, the metric distance between particles, between points in space, is a dynamical physical entity, sourced by energy and curving. But string theory has, and our attempt to unify the forces, has led us to question even that sophisticated version of space and time. And has brought up all sorts of questions like, are there more than 3 dimensions? String theory, sometimes in the way we look at it, requires that there exist 6 extra dimensions. Which is very interesting because in certain solutions of string theory or realizations of string theory, many of the structure of our understanding that we can't explain, like the nature of the forces, the forms of matter, the kinds of matter we have, their masses, are all determined by geometry, by the geometry of the extra dimensions that are invisible because they're curled up into small manifolds, as pictured here. But the real problem has to do with the quantum structure of gravity. As I said before, Einstein says, gravity is nothing more than the dynamics of space-time itself. And when you have something dynamical in quantum mechanics, then it fluctuates like those fields did in vacuum. So in quantum mechanics of gravity, space-time itself is fluctuating. When you think of space and time, they're fixed, right? There's just space, you know. And then time is just a clock running. But what does it mean, fluctuating space-time And when these fluctuations become big, sometimes called space-time foam, we really lose control over what we're talking about. So this is a challenge, one that string theory has met head-on, with very interesting results. The other place where quantum gravity becomes important is when the gravitational force is very strong, like in a black hole. A black hole, in Einstein's theory, is a region of space where there's so much matter that light can't escape. You take a beam of light, you shoot it up, and it goes up, falls back. The gravity is so strong that light can't escape. So if you're outside the black hole, you can no way ever get any information as to what's going on inside. Now, black holes, that's pretty strange and weird. And for a long time, astronomers thought black holes were crazy inventions of crazy theorists. But by now, they have observed and measured, and they know that their universe is full of black holes. Every galaxy has a black hole at its center. Our galaxy has a black hole which weighs 1,000,000 times the mass of the sun in the center of our galaxy. And we can see stars going around that black hole and measure its mass, but there's nothing there. And recently, LIGO has made the first observations both of gravitational waves, waves of curved space-time, as well as the first observation of merging black holes. This was done at 2 interferometers. These are long tunnels, a few kilometers. This one is in Louisiana. There's one in Washington State. Light goes back and forth. And if a wave of gravity, which is a wave of space-time, passes through, it could lengthen this arm and shorten the orthogonal arm, this arm, change the interferometer, change the interference pattern of these lights. Enough, and this interferometer is so precise that it can measure the change in the length of this tunnel by a fraction, 1 part, I think, in 1,000 or more even, of the size of 1 proton. Totally amazing. And when this final version of LIGO turned on, within the first week, they were lucky enough to see an incredibly violent event that happened far away in the universe. We're not exactly sure where, sort of roughly, 1.5 billion years ago, when presumably 2 black holes, this one was about 50 times the mass of the sun, this one 30 times the mass of the sun, attracted together, merged, and then settled down to a bigger black hole. In that process, about 20% of the mass of these black holes was converted into energy in a period of about 1 second. In that 1 second time, this merger was emitting more energy than the rest of the universe combined. It's a very violent event. That energy was emitted in the form of a wave of gravity, a wave of ripples in the curvature of space-time, which spread out. 1.5 billion years later, it arrives at Earth, passes through the interferometer, and you see this signal. There's a blue signal from Louisiana and a red signal from Washington. They agree precisely, and they agree precisely with a theory of Einstein, of the merger of these black holes. You can see the merger, and you can see the ring down. They form a big black hole which settles down, ringing like a bell. This is going to turn out to be an enormously powerful astronomical instrument that will allow astronomers to probe black holes, the merger of black holes and of other objects throughout the universe in the years to come. Black holes are also good for theorists like me. They provide paradoxes, because strange things happen with black holes. And if you drop something into a black hole, well, you have no access to it. You've lost information. If I drop a book into a black hole, well, nothing can come out, so I've lost that information. But Hawking noticed, Hawking famously, it's what he's famous for, he is saying that black holes are in quantum mechanics, the quantum mechanical world, evaporate. They behave like thermal objects emitting light, and eventually they will lose all of their energy, their mass, and disappear. Might take a long time, but they're not forever. And then the problem is, what happened to the information that you dropped into the black hole? And Hawking challenged quantum mechanics. He said, black hole formation evaporation violates one of the basic principles of quantum mechanics, that you don't lose information. Information is preserved. And we now can more or less confirm that within string theory. We have learned that string theory allows us to formulate a duality between theories of gravity with black holes and ordinary theories like QCD, which describe quarks and gluons. Don't have time to explain that. String theory also has challenged, however, space and time in a very basic way. It asks, we now ask, and most of us, or many of us, I don't know, all of us, but many of us believe that space-time that we invent as infants is a little too crude to deal with the problems of quantum gravity, of black holes, of the origin of the universe. It should better be thought of as an emergent concept. In other words, it's not the way we should fundamentally formulate our theories of physical reality. It rather is a crude way of describing pretty good at most distances in most situations. But when we begin to ask a question like, how did the universe begin? What happened before there was time? Et cetera, it probably is not a good idea to use our conventional notions of space-time. And we're beginning to develop, in very special toy cases, understanding of how you can, how space-time can be a good emergent concept, although not fundamental. In a sense, we're beginning to ask the question and construct conceivable answers. What is space-time made out of? What is gravity? How is gravity emergent? Well, I'd like to finally talk about more ordinary physics, or condensed matter physics, atomic physics, molecular physics, in answer to a question which might arise. It's all fascinating, wonderful, but you know, especially as Singapore is a very practical society, what is this good for? And I'm sure many of you have heard about Faraday's answer. Sir Michael Faraday, who is the guy who really discovered the basic phenomena of electricity and magnetism, his answer to Queen Victoria when she visited his laboratories and saw all these marvelous magnets and electromagnets. And she said, all very interesting, Mr. Faraday, but what is it good for? And Faraday, of course, had no idea. He didn't know what electricity and magnetism would be good for. He didn't know about motors or currents or electrical lights or the Industrial Revolution. He really didn't. He was just having fun and trying to understand, you know, electricity and magnets and their connection. So he said, I don't know, but when we find out, you will tax it. So what is this all good for, this theory of the nuclear force, or our even more ambitious studies today? I don't know either. No one knows. With the most fundamental research that leads to the most fundamental advances in technology is never or rarely discovered as an answer to some given project of some government or corporation. And the best example by far in recent times is quantum mechanics. Quantum mechanics is this weird new way of looking at the world that was invented to understand how atoms worked. Now, those people who invented quantum mechanics could have thought of applications, but they would not have dreamed of what we've done with quantum mechanics. Planck and Einstein and Bohr and Heisenberg and Schrödinger and Dirac. Quantum mechanics is about nearing 100 years old. It's about 90 years old now. And it totally dominates modern technology. The uses of quantum physics are manifold, from transistors to lasers to integrated circuits and many more, superconductivity. All of our modern gizmos and much of our technology is now based more and more on our understanding and ability to control quantum physics. But I'd like to tell you that this is just beginning. This is only a theory, an understanding that's 90 years old. It's a very short time. There are people who were born living today before the invention of quantum mechanics. We are now beginning to understand and control the physics of individual atoms. Understand and control, they go together. We can now see atoms, we can pick them up, as I showed before, we can create new materials of all types, and we can begin to create new forms of matter with many, many different purposes in mind, many applications, in two ways that are truly new. One is sort of old, putting together atoms to form molecules and molecules to form other molecules by chemistry. That's what chemistry is. Transformation of molecules to form new molecules. Now, the way people do chemistry by and large is trial and error. You look for the right enzymes, the right conditions, you try to manipulate the chemical reactions. But now, more and more, we're able to do calculations. We know the laws. We know the equations. They're just too hard to solve. But with good computers and better theoretical methods, we can create new chemistry, improve on our chemical by quantum control of the process itself with the help of lasers and the help of theoretical calculation. But the other frontier of creating new kinds of matter with new purposes in mind is what's called sometimes nanoscience or nanomaterials, relying on the increased knowledge and ability to manipulate ordinary solids and heterostructures and disordered materials at the atomic scale. So what is this good for? Well, the list of things it can be good for is enormous. But the one that is most out there and driving much of the fundamental research is quantum computing. So a lot of our great advances in science and technology and in society is based on Moore's law, on this incredible exponential growth of computing capability over the last 30 years. But Moore's law and this growth is nearing an impasse because we're getting to chips whose basic components are the size of atoms. And then quantum mechanics becomes crucial and bottlenecks arise. So one hope to get around this problem and continue the expansion of our computing capabilities is quantum computing. Now, quantum computers are somewhat similar, I mean, at a very conceptual level, to classical computers. Classical computers, as you know, manipulate bits of information, zeros and ones. Quantum computers manipulate quantum bits. You could have a physical system that is in two possible states. The simplest example being a particle which is spinning one way, clockwise, or anti-clockwise. We say spin up or spin down. But in quantum mechanics, you can do something you can't do in classical physics. If you have a system with a spin up or spin down, you can construct a state which is, we say, a superposition of spin up and spin down, a state where it's neither spin up nor spin down. If you measure the spin of this state, it's 50% probability that it's up, 50% probability that it's down, but you can construct this sort of superposition. And that means that qubits can be infinitely more powerful and contain more information than classical bits. It has been shown that if you could construct a computer, a device, that manipulated qubits as opposed to zeros and ones, there are some calculations you could do, and probably many, this is only beginning to be explored, exponentially faster than classical computers. And the one that caught everybody's attention, especially the government, 20 years ago, was a demonstration that if you had such a computer, you could break all the codes in the world. They're all based on factoring large numbers. Factoring numbers is very difficult. And quantum computers can do this much faster. That caught the attention of the National Security Administration. And so a lot of effort is there because people are worried about breaking all the codes that you use to communicate over the internet or spying on other people. But there are many other such problems that we need more interesting problems than breaking codes that we need quantum computers for. For example, understanding in quantitative detail quantum chemistry. If you had the power of quantum computers, then it's easy to simulate or calculate the properties of a quantum system like a chemical reaction, and then use lasers to control it. Microsoft is now investing hundreds of millions of dollars in constructing, in my opinion, a little prematurely, a factory to start building quantum computers which haven't yet been truly designed. And we don't even know that they're possible with the methods that they're imagining. But they're very interested. And there are problems like nitrogen fixation. Goes back to, what's his name? Fritz Haber, who won the Nobel Prize. That is a incredibly multi-trillion-dollar industry with something like somewhere between 5 and 15% of the energy of the world goes into fixating nitrogen, which we use for fertilizers. And chemists have been trying to improve on the process invented by Haber for the last 100 years to no avail. And the stumbling block appears to be the understanding, well, people would like to think they can improve it because bacteria can easily fixate nitrogen with very little energy. But we don't understand how they do it, and the obstacle there is mimicking the quantum chemistry of the relevant proteins that the bacteria use. It's just too complicated a problem for classical computers. And there are many such problems. So it might be worth investing a few $100 million, even if no one has yet told them how to build it. The problem is that quantum systems are very fragile, which is why quantum mechanics is so weird, because we live in a classical world to a very good approximation. And that's because if you take a quantum system and you let it interact with the environment, it behaves classically. So you have to protect it, and that's very difficult. So there are many, many attempts to try to construct such quantum computers, and this will be done. The only question is it 10 years, as Microsoft is imagining, or 20 years, or 50 years? But it will happen. So even atomic physics, molecular physics, physics of ordinary matter is, although the basic laws are well understood, the understanding and control in a serious way, in my opinion, is just beginning. The prospects for the discovery of new matter and the creation of new forms of old matter are extremely exciting. Some people say physics, the 20th century was the century of physics. 21st century is the century of biology. Well, to some extent that's true. Biology is a very young field. Many of the basic phenomena and applications are just around the corner, no question. But in the end, even biology is really physics. It's the physics of living matter. And there's no question, in my opinion, that physics will continue to be very important, and the best is yet to come. Thank you. And I talked so much that, unfortunately, that there'll be not so much time left for questions, right? But maybe a few.
3 questions. It is your time now to ask whatever question excites you, because our speaker, he is not bound by boxes. He is ever ready to look beyond his own little box. Right? So we want to look beyond this box here. If any questions, you can come to the microphone.
Hi, good evening. Thank you so much for being with us today and for this really, really inspiring talk. I had a question for you. I actually had 2, but I'm going to keep it to 1. How far away do you think we are from being able to create fundamental particles inside a lab?
Fundamental particles, what?
In a lab.
We do all the time. We have to start with something. So we start typically with protons or electrons and positrons, sometimes matter and antimatter, sometimes matter and matter. And when they collide, we process the forces, interactions between the quarks or the electrons and the positrons can convert the kinetic energy of this very energetic collision into new particles. So by and large, that's how for the last 50 years, or more like 70 years, we've been exploring the properties of nuclear matter by colliding protons together, creating new particles, seeing how they decay, how they interact. So this is, we do it all the time. It's very, you need a lot of energy. You need an energy which is bigger than the mass times c squared of the particles you're looking for. So that's why we build bigger, more and more energetic colliders to create even heavier particles that we haven't yet observed. Most of the particles we create are unstable. They can decay to lighter particles and lighter particles, and that's why we don't see them lying around in this room. So we need to create them in these collisions. But I'm not sure, was that the question you were asking? Because we do this every day.
Right. I guess in terms of not only creating them, but also being able to control them, as you said.
The problem is that they are typically unstable. You know, the neutron, the well-known part, you're made out of more than half the particles. The mass of your body comes from the neutrons in the nuclei of the atoms you're made out of. In free space, those neutrons are unstable. If I take a neutron, and you in the laboratory, and you put it in a box, and you wait 11 minutes, 50% probability it will have decayed to a proton, an electron, and a neutrino. So if you wait long enough, most of these particles will turn into lower mass particles. The only ones that are stable, or maybe they aren't even stable, are the proton and the electron and the quanta, the particle of light, photons. Light is moving at the velocity of light, so it zooms by. Proton can sit on the table, and we think, and it's pretty stable. However, in our unified theories, even protons won't last forever. As Shelley Glashow said, diamonds aren't forever. But we know that protons will at least last for 10 to the 34 years. That's a long time. I mean, the universe is only 10 to the 9 years old. So you might ask, how do you know that the proton lives longer than 10 to the 34 years? Well, you take 10 to the 34 protons, and you put them in a tank, and then you wait 1 year. So then one of them will have decayed, and you look for that signal. And that's how people look for the decay, the instability of the proton. But for all practical purposes, protons are stable. Electrons, we believe, are stable. Everything else is unstable. Even the carbon you're made out of is kind of unstable. If you wait long enough, we would believe that all of the nuclei would turn into lead. Lead is about the most, or iron is about the most stable nucleus. So it's just that some things live longer. The particles we make in the laboratory, some of them live for a billionth of a second. Some of them live for a billionth of a billionth of a billionth of a second. Now you might ask, how the hell can you see a particle and measure its properties if it only lives for a billionth of a second? Well, it's not easy. But it's been done. It's quite amazing how we've been able to make this much progress and learn this much about such invisible, difficult to observe particles in just a period of 100 years.
Thank you.
And much of it was funded by some government. So Queen Victoria didn't just tax it, she actually also funded it.
Yeah.
So let us give thanks.
Because Queen Victoria and her successors realized that this sort of curiosity-driven research comes up with things like quantum mechanics, which have unexpected and unlimited payoffs in the future.
Okay. Oh, yeah, right.
Sorry. Yeah, sure. You want to have the mic first?
Rush.
Then
Oh,
I'll go
yeah.
next.
Isn't it great that God has created us? And we
Maybe.
still discovered. Thank you.
Oh, so that was not a question, that was a comment. Right? But anyway, let's
Yes.
have one last question.
I have a
here.
question. Thank you, Prof. Gross, for being in Singapore and giving us a talk. I was enlightened at many times during your speech, and humored also sometimes at some of the comments that you had made. I've got actually two parts to my question. The first part of the question is, you talked at the end about space-time and gravity possibly being an emergent concept. So my question there is, do you think that probably matter could be an emergent feature in this whole matter, the concept of matter, could be emergent also? Second question is, in terms of the nature of reality that we have discussed, or you have presented, fundamentally it's composed of matter, quarks, etc. But we can understand that we have consciousness, which on this scale, on a biological scale, we can experience it. So in the cosmological scale, in the large scale, what role does consciousness play in the theory of the universe? Thank you.
Okay, well, if we, in the end, find a formulation of physics that in which space and time are not fundamental, then everything sort of changes. The way we describe matter, or just about anything in physics, is we assume some underlying structure of space and time from the beginning. But, you know, what we call a particle or matter can already shift. In fact, in string theory, particles are states of the vibrations of this extended object and not point-like objects like atoms or quarks or leptons. And so our current well-tested theories are of point-like particles, quarks and leptons. But we continue to look at quarks and leptons with even better microscopes to see whether there's any structure. And the history of physics is discovering that what appeared to be point-like objects had structure. Atoms are made out of smaller objects, electrons and nuclei. And then nuclei are made out of smaller objects, protons and neutrons. And then protons and neutrons are made out of smaller objects, quarks. And for the last 30, 40 years, we've been looking to see whether quarks are made out of smaller objects. And no indication that there are smaller objects inside the quark yet. But, for example, a good picture might turn out to be like string theory would suggest that if you looked with even better microscopes, you would see not a point-like particle, but a string. And we don't know for sure. Now, about consciousness, there really is no relation that anyone has ever found, although lots, between life and conscious life and the physical laws of the universe. As far as we can tell, there are no forces. There's nothing, let me put it very strongly, there's nothing that we have observed or suspect in biology, in living matter, that is not explained, could be explained by chemistry, by atomic physics and chemistry. And biologists now are well on their way to explaining all of life and how it works using, if you want, in a reductionist sense, our standard theory of physics, of atomic physics, molecular physics, biochemistry. That's it. I believe that's probably the case. Now, the hardest problem, of course, in biology is the brain and is neuroscience, how the brain works, and the various phenomena that we experience in our own existence. Many of which I believe are our impression of them is rather faulty, and in particular consciousness. So to try to understand consciousness in terms of biochemistry is not going to be easy, and it's made even more difficult by our immediate perception of what the brain does, much of which neuroscientists are beginning to question whether our experiences or what we imagine our consciousness, our identity, our I is not how it really is working.
Thanks, Prof. Just a quick follow-up on that. What's the difference between matter and living matter, according to you?
Well, living matter is biological matter. What is very different between the kind of, I believe there's no fundamental difference, except that the following sense. Most of the systems that physics understands well are systems that are closed systems, often in equilibrium in static situations. Life is from very essence a part of a system, an open system, where where order and patterns are created without violating the second law of thermodynamics. So entropy is increasing, disorder is increasing, yet part of the system creates structure and complex structure to life. And the other important big difference between the kind of physics that we're used to in non-living matter is the difference of living matter compared to non-living matter, say the behavior of a liquid or a solid or passing electricity through a material, is that in biological systems, information plays a crucial role. So biological systems are systems which create order in lots of information, negative entropy, which in our case is embodied in the nucleus of our cells in the DNA. That information persists and influences, helps create this structure. And there are very few systems in non-living matter where the information is such an important part of the development, of the time development of the system. So it's a very unusual system. There are people who are trying to understand whether the emergence of life on the Earth is kind of accidental and rare, or there are certain types of open systems with energy sources, like existed on our planet, which in which the emergence of complex structures is likely, is not unlikely. But nobody knows, and nobody knows how life originated on Earth. And but I, as a physical physicist, believe strongly that it's all it is in the end is atoms, electrons and protons, quantum mechanics, and the force of electricity.
Well, that's